Hi, it's teardown time again. Today we've got a real sexy bit of kit. This is a Marconi Instruments 2023 1.2 gigahertz signal generator. Oh, I love it. This one's going to be fun. Lots of porn in here. Let's check it out. And you should know the name Marconi. Yes, the famous man himself. And that led to a whole bunch of companies, including a spin-off Marconi Instruments. And interestingly, I used to work back in the day at GEC Marconi. Go figure. Anyway, they used to make some really top-end, highly reputable RF signal sources, generators, all sorts of test gear like that. So very famous names. So I expect a whole bunch of top-end, very well designed hardware in here, made in England. Beauty, the old dart, ripper. And they were sold sadly to IFR Systems, I think back in the late 90s or thereabouts, and in the early 2000s sold to a company called Aeroflex. Huh? Go figure. And apparently they still sell this. You can still buy the 2023A. Looks exactly the same. It's probably got a few little upgrades inside, but you can still buy the same instrument today, more than, I don't know, at least 15 years later. Fantastic. I think we're going to enjoy this one. Let's check it out. Oh yeah, you can smell it. Top end hardware. And I thought I'd just show you it powered on first, because look at this beautiful backlit dot matrix display. I'm not sure how well it's going to show up on video, but it's a really bright, really fantastic display, almost like a vacuum fluorescent display. Keypad interface, external modulation input over here, 9 kilohertz to 1.2 gig frequency range all up, and it's got the low frequency modulation output and the RF output, of course, which is an N connector, but I've got an N to B and C on there, and of course it's got to have a knob. Beautiful. And check this out. If we hit the carrier frequency button here, we can actually adjust this thing in 1 hertz steps from 9 kilohertz all the way up to 1.2 gigahertz. 1 hertz steps. You've got to be kidding me. So let's go up to a gigahertz there. There it is. 1 gigahertz, and we can still go up in 1 hertz steps. Beautiful. It's got 2 different types of modulation as well, which you can actually mix together, as well as with the external modulation input over here, and it really is quite a versatile RF signal generator. I love it. And the RF output can go anywhere from plus 13 dBm to minus 137 dB. Beautiful. And with this puppy, of course, we can check the bandwidth of our Agilent InfiniVision 3000X series scope here, 500 megahertz bandwidth scope. Let's check it out. I've got a 10 megahertz signal I'm feeding in now at about half a volt RMS. So let's try and find the minus 3 dB frequency of this thing. You'd expect it to be 500 megahertz because that's its quoted bandwidth. So expect it to drop to about 350 millivolts or minus 3 dB, 0.707 of 500 millivolts at 500 megahertz. Let's give that a go. Let's up the frequency directly to 500 megahertz. There it is. And check it out. It's only 400 odd millivolts, so it actually does better than that. So we're going to have to up the frequency here and see what happens. So I'm going to up it in 1 megahertz steps until 450 or 453 or thereabouts. There it is. And that's 637 megahertz. Beautiful. And just as a little heads up, Agilent are going to actually upgrade this scope for me to the brand new 1 gigahertz option. So it's going back to Melbourne. I'm going to be flying down there in the coming months, and we'll see, hopefully see this puppy being upgraded to 1 gigahertz. So stay tuned for that one. Alright, I know you're curious to see it. Let's wind the wick up even further. Let's go. Can it display our 1 gigahertz signal? It certainly can. Can it go to 1.2? Oh, yeah, but now we're really right down in the noise. But interestingly, the hardware frequency counter is still spot on. And on the back here, we've got, there's a sticker that says no options fitted. Bummer. So this thing comes with various options. One of the real good ones is the really high stability temperature oven controlled oscillator. So I don't have that. What a bummer, but doesn't matter. I've got those in my lab anyway. And check it out. Made in England. How often do you see that? The old dart. Brilliant. And of course it can be controlled by RS-232 or IEEE, and it's got a standard IEC mains input connector. It's got various other DC inputs and a RF output on the back, optional, which I haven't got, or a DC supply if you want to use it in some sort of remote location or something like that. But that's about all you got on the back. Now it's time to crack this thing open. And that came open pretty easily, exactly as you'd expect instrument of this type too, with the case just sliding off the back like that after a few screws. And check out what's up here. There's a loose bit of, paper. Let's check it out. I wonder what it is. Unbelievable. It's maybe somebody's serviced it or done something. What is it? It's a data sheet. For a transistor. What the? Why on earth is that stuck inside this thing? Nothing on the back. That's bizarre. And as for the unit itself, this is pretty much the construction I expected. The power supply is huge. It takes up almost the full length and the full height of the unit. So that's massive. I'm a bit surprised at the size of that power supply. I guess they're going for ultra high reliability, I guess. One big digital processor board on the top. It's got the main frequency crystal here we'll take a look at. And, you know, a coax or two going around, but all of the RF magic is contained in a can on the bottom there, presumably. Exactly what I expected. And let's take a look in the power supply section. And it's not really as big as I thought, but here's the main board here, but they've also got the backlight inverter in here as well, and they're basically just using it as a big shielded cage pretty much. There's a bit of wasted space over here, but apart from that, that's pretty much what they're doing, is just shielding this sucker. But they've also gone to a lot of trouble on the finer points of the engineering in here. So let's take a look at it. Now, these power devices attached to the side of the case, they're using the side of the case as a heatsink. They've gone to the trouble to do a custom folded aluminium bracket there, massive amount, and there's a secondary metal black bracket behind here as well. And they've used some very professional looking clamping mechanism for the devices, all individually screwed. They've got some sill pad material behind there. Very nice. There's a couple of linear voltage regulators on there, plus a couple of switching components here and over here as well. And they've just gone to a lot of trouble to actually heatsink those very professionally on the side of the case. I like it. And the transformer here, as you'd expect, it's professionally mu metal wrapped there just to try and keep the leakage from that down. They've got another heatsink device over here, and they've got 4 output filter caps here, because probably for redundancy and stuff like that, they're not just relying on one big one. They've got either 2 or 4 separate ones, or possibly due to the massive inductors in here, probably some extra low frequency filtering as well. And the main capacitors have been gunked down so they don't vibrate. Unfortunately, this little vertical riser board here could actually vibrate a little bit, but look, they've gone to the effort to put the plastic spacers on a good lot of the high powered resistors and diodes on this board. I really like that. No surprises though, the power supply is actually made in Taiwan by a third party. Well, you can't have everything, but that's fairly typical of these devices, but they've put a lot of effort into this supply. And here's the power switch on the front panel there, and they've gone to quite a bit of effort to actually make this shielded, and the shielding is connected down there, properly crimped and properly locked in place with a shaker-proof nut, and it's really quite nice just to shield the mains wiring going from the back to the front. I really like that. And they've got more grounding on the heatsink plate here, which goes into here, and also the earth, they've got that going down to the plate down the bottom, once again, also with a shake-proof nut and professionally crimped. And there's the other end of the mains cable. Once again, the shield for that is also connected at this end as well. And check out the rubber boot. They've got complete, like a heat shrink rubber boot going over the IEC power connector. Brilliant. And this device down here, that looks, to me, for all the world, like one of those temperature cutout things. So maybe if the temperature of this plate gets too high, it's just going to cut out the mains input. Beautiful. I don't think I've ever seen that on a bit of test gear like this. And one thing you'll note on the back of the case here, they've got this metal stuck on metal braid like this to get good RF screening between this and the back and the top, the outer cover of the unit. Nice attention to detail. They're really serious about keeping things out, keeping RF out of this and keeping it in. And there's the LCD backlight switching board. Nothing really exciting going on there, but they've put it inside this the same case as the switching power supply to keep shield it from the rest of the circuitry. Great. And the power supply output wire in here, they've got a couple of ferrite beads on there for RFI. And those beads there are actually matched with these ones on the input to the board down there. Check it out. And there's a nice standard flat flex rainbow ribbon cable there going from the digital board to actually penetrate it. They use a D9 connector, a D25 connector here to penetrate down through into the RF section of the board. Another rainbow ribbon cable going to the front panel here for all the switches. And there's another rainbow cable in the back of this board which actually connects everything from one side, this board over here, once again through to the front panel board. And construction of the main board is fairly typical of the era. We've got PLCC packages here for various devices, and the rest of them are just standard SO packages. So, you know, we're talking 95, 96 vintage here. They've got one DIP 40 package up the top here, but apart from that, it's, you know, they've used all SMD electrolytic caps all around here. Totally, almost totally SMD design. I like it, but they've got a socketed EEPROM, of course, still fairly typical of the day because they're using a micro processor instead of a microcontroller which has flash firmware. They've got good old-fashioned EEPROM. Love it. And of course there's the obligatory bodge wires around here, green mod wires, maybe to try and match in with the green solder mask on the PCB perhaps, but they're near some HC OOs. There's a lot of 7.4 HC series TTL stuff on here. And we've got an Analog Devices ADSP 2100 series microcontroller slash DSP. It's optimized, essentially a microcontroller optimized for DSP type work. 25 MIPS or thereabouts, nothing earth-shattering by today's standards, but that would have been a relatively powerful beast back in 1995. There it is, 41st week 95. So that dates this board to very much towards the end of 95, possibly early 96 manufacture. And we've got a HiQ brand, very popular for the age, TCO 768 10 MHz reference oscillator. Now, this is the temperature compensated oscillator. It's not the extra option oven stabilized oscillator. You got to pay, I don't know, $1,000 or a couple of grand more for that option. And look at what we have here, an Intel ADC 188 processor, and we've got the EEPROM to go along with it. So they've clearly split the processing functionality between the Intel processor and between the Analog Devices DSP we saw before. We've got another Atmel EEPROM device up here. We've got some SRAM, and this device over here is an NEC 7210 GPIB controller, and that's about all she wrote for the processing part of this thing. And this Texas Instruments TL16C452, it's a Centronics printer port interface and dual UART as well. So it's one of those sort of, you know, all-in-one LSI solutions for Centronics and Serial back in the days of the IBM PC. And here we've got an AD7537 dual 12-bit DAC and support circuitry with those caps up here and stuff like that, and it's obviously part of the modulation capability, because the external modulation inputs are up here like this, and so obviously that's part of, I'm not sure if it's all of the modulation capability, but it's at least the high level modulation capability of the board. And we've got some power supply stuff around here, and we've got an AD586, that's a 5-volt precision reference right there. And that's probably about all there is to the main control board. And if you notice the front panel end connector down in there, it doesn't have a shielded coax at all. Instead, it's a proper metal tubing. There might be coax inside that metal tubing, but they've really gone to town. They're not just relying on the braid of the coax itself. They're really making sure and using that as a full metal tube, and that runs all the way over to the other side here. And here's just another view of that tubing going from the end connector on the front panel there, all the way across down into the RF section. And check out the RF section. There's an awful lot of screws and stuff on this thing. Whoa, this could take some effort. Uh-oh, this module contains beryllium oxide components. Refer to handbook. Screw the handbook. Well, it seems like I've taken off possibly the wrong side, because there's a, this is all die-cast aluminium here, and so all the screws on the bottom obviously hold in the board. On that side, all these center screws, they're all molded. It looks like they're all molded into that die-cast, but there is this top aluminium plate with all these screws, so maybe it's a dual-side access board, this plate here. I expect if I take off all these screws, we should get access to at least some circuitry under here, with the bulk of it being accessible on the other side. Oh yeah, smell it. RF porn. Just as an aside here, look at the this whole die-cast plate here. They've actually built in the standoffs for the top PCB into that here and here. So that, you know, that's a lot of system engineering which goes in there to ensure that, you know, that this whole thing is assembled and constructed, you know, so that the mechanical people who design this talk to the PCB people who are laying out the board, talk to the system engineers who are actually laying out, you know, designing the architecture of the thing, and it's just a lot of work. But ta-da! Here we have RF magic. And one of the first things you'll notice is that all this circuitry is embedded in the die-cast can here, and it's surrounded by this what looks like a rubber seal against the top plate. But if we take a look at that, so let's actually probe what that stuff which looks like rubber down there, and It's not. It's completely conductive. And there's no surprises really. This construction, you've seen it before in my teardown of the Tektronix mixed domain spectrum analyzer scope, and it's very typical of RF system design like this. It's very modular. They're actually broken down into modules, and you can physically see them, and you can actually see the controlled impedance traces, and check out the heavy number of bolts they've got tying down the board in each section. It's absolutely incredible. And if you look closely, you can see the penetrators going through to the bottom module down in here. So these penetrators are all the way along. They're tapping points off. They're either injecting stuff in or they're tapping stuff out down to the bottom RF section of this board. I love it. It's brilliant. And what we've got here is clearly the output board, because if you look down in there, there's the that RF tubing going to the end connector on the front panel, and it goes into a Pickering RF relay here. That thing wouldn't be cheap, let me tell you. It might be $100 or something like that. Wouldn't surprise me at all. So there's obviously some power protection circuitry in there which trips the relay or something like that. Now what I've done here is I've flipped the board around so that the output is over here to match the system block diagram. And if we show the system block diagram on top of this, it might actually make some sense. Here's the output reverse polarity protection here. We've probably got the step attenuator here. We've probably got the pulse modulator here coming through one of the penetrators there, the input to the pulse modulator and the input to the step attenuator perhaps. And then going along further, we might have the BFO, the two BFO switching sections with the input. The BFO is actually probably on the bottom board down in there, but they're just the switch sections for it. And then over here we've probably got the level modulation and probably the AM modulation too. So you can see how that's probably making sense now based on the block diagram, and that's probably how they design this thing. You start off with a high level block diagram, you go into little building blocks, and then you're going to lay out your board pretty much exactly the same way that you see it. And you can shield the individual sections, because you see the shield actually comes down in between here with just a little penetrator down there for the trace going across there. And it just, you know, it just all works based on the overall system diagram. And on second glance, that does actually match up perfectly, because these are relays. Look, they're on the underside of the board, but they're RLF. So it's relay F, and they go along and they number it D, E, F, G, H, E, and it goes so forth right up to the Pickering relay, the Pickering output relay over here, which is RLM. There you go. So these are those switching boards. So it matches up precisely. The individual blocks match up exactly to the system block diagram. I love it. And I love how you can just see the main signal flowing through that center conductor, that center microstrip conductor there. This would be a controlled impedance board, of course. They would have paid very close attention to that. It's probably not even FR4 material. It would be some sort of, you know, a Teflon board or something like that, some sort of high frequency, better controlled impedance board than FR4. But you can see the microstrip run, the signal run straight through. And then they've got these shielded bits and sort of like a penetrator here between each section like that, so that just the microstrip trace goes through. Brilliant. Now this part here is rather tricky. I can't get a socket down in there to actually undo those screws, so you've got to actually shift. There's a couple of screws on the side here, you've got to loosen them, and the whole thing actually just slides out a little bit and comes out more into that open notch. Well, I don't know why you just didn't put the huge notch in there. Anyway, that's a bit tricky. Ah, here we go. This is going to be good. Bloody hell of a lot of screws on there. Someone was really fond of these long black screws, which presumably go down into the die-cast walls to separate all the modules. Here we go. Oh, crikey, check it out. Beautiful. Oh, I love it. There it is, warning, beryllium, under that RF transistor by the looks of it there. So there you go. That's about all they've got in here in terms of beryllium, and they marked it on the silk screen. Brilliant. And once again, no surprise, typical RF layout. It's all modularized, and they've got this alloy shield inside. That's not part of the die cast. I can actually lift that out if I wanted to. It's one big board. It's one big PCB, but with shielded parts, and they've even gone to the trouble to shield inside the shield. Crazy, but there you go. That's the effort they've gone to. There's a big tag down here to connect to the upper plate, as if all the screw holes and everything else wasn't enough. They had to actually attach it at that point down there as well. And no doubt, just like the board we saw on the upper side, if you got out the rest of the block diagram and looked at the rest of the modules that we have left, you'd probably find that each one of these mapped to an individual part of that system block diagram. And interestingly, here's the penetrators along the top here, and they're just rainbow ribbon cable down to the 0.1 inch header down there. And these penetrators obviously are like DC signals. They're not RF signals. They're just DC control voltages or low frequency modulation signals or something like that. So they don't have to go through like a coax or anything like that. They happily do it using ribbon cable. Now this section here goes through these penetrators into the AM modulation top far end part of the board, and there's a DAC here, so that obviously contains the RF level DAC and the AM DAC as well inside this section. The harmonic filters, they're probably over on this board over here. And this board with the warning beryllium compound, these are probably the harmonic filters in this section of the board, and you can see those on this system block diagram. And one of these in here is probably the top octave processor or something like that, maybe the local oscillator, the voltage controlled oscillator perhaps, or maybe that's in one of these sections over here. But I'm sure if you put a bit of thought into it and studied the block diagram, you could easily figure out which module is which. And down here we have a Xilinx SP8402, and that's a very low phase noise divide by N device. So there's our divide by N part of the block diagram, and it probably contains the top octave processor in there as well. And here's another Xilinx device. It's the SP8400 as opposed to the 8402 we saw before, and that is once again a very low phase noise device, and it's the fractional N synthesizer. So that's the fractional N synthesizer block that we saw in our system block diagram. Easy. And this section in here, well, we've got a Philips PM7543 DAC. So that's probably this part of the system block diagram with the attenuation with the modulation converter and the step attenuator and stuff like that. And I've taken the shield off those cans, and that's probably the VCO over here perhaps. So that is in that part of the overall system. So there you go. That's a rough functional block breakdown of this device. I love it. And once again, it clearly follows the system functional block diagram. It's really neat. And when you're designing these, it just really helps to modularize these and keep them separate like this. Not only does it make sense from a shielding point of view and a layout board point of view and all that sort of stuff, but really it just makes sense from a system debugging point of view, testing, all that sort of stuff. But really, they've done well to get all this RF magic onto the one board. There's a lot of effort there. Each individual subsection would have to been individually tested and characterized and stuff like that before they did the final layout. And up here it says it's only issue 2 of the board, although there's another box next to it which says issue 8 in a pen. So maybe they've gone through a few revisions. So I hope you enjoyed that, a teardown on the Marconi 2023. Lots of RF magic in there. I love it. brilliant. And if you liked the video, don't forget to give it a thumbs up. If you got any comments on what you think parts of these circuitry do, I haven't gone through it in detail at all, then by all means, leave it in the comments or jump on the EEVblog forum and talk about it. This has been a rather interesting bit of kit. I'll catch you next time.